Welcome to the lecture number 67. So, today we are going to discuss about the stability of the magnetically actuated satellite system. So, in that context, what we require that we need to apply as I have told you that in the system dynamics, this matrix is similar, that is this is of rank 2, and therefore, as a at any instant of time, this system is not controllable. This is what we have observed in the last class. Okay. However, if we average the control matrix, gamma and write as gamma bar is the average gamma, okay. Then the system is controllable in an average sense. So, to apply the averaging theorem, it is required that system dynamics, which can be represented as x tilde equal to f x tilde times t, f x tilde t, where why we are writing this, because your this part is time dependent. Okay. Therefore, we are writing here as this. It is required that this be casted in a standard, this is non autonomous system, in a standard non autonomous form. So, this standard non autonomous form, it looks like x tilde equal to f x tilde t epsilon. So, why this epsilon is appearing? This equation can be changed. Okay. Here let us write this as f 1. So, that we use f here. So, the previous equation, this equation can be changed and recasted in terms of other variables. Okay. Let us say that instead of writing here, we write as z tilde epsilon f z tilde t epsilon. So, we can cast it in a new format, okay, where the epsilon, which is a quantity lying between 0 and 1, it appears like this. If it happens, so in that case the dynamics becomes slower than the excitation. So, for the averaging, as I have stated you earlier, that if the dynamics is slower as compared to the excitation, what you see here, that excitation is very fast, and because of that the system response is like this. So, we can replace this trajectory by this averaged one. This is the averaged one, which is shown like this. Okay. And thereafter, once we have casted here this in the non-autonomous standard non-autonomous form. So, this can be then changed to a standard autonomous form, which will appear like this, and this will be your, you can write as f averaged instead of f here, this will be f averaged, and this will be in terms of z tilde. Okay. So, this is your giving the average dynamics. And then you can apply the Lyapunov theorem to this to prove stability of the average system. So, definition of the averaging theorem, it states like a continuous, how do we define the average system? Non-linear system or the non-linear function this exists. So, this is the averaging of this is the way of averaging any function. So, this is averaging in time domain, it can be averaging in space or whatever, it depends on the type of function. This stands for the t here, this particular interval 0 to infinity, and this d is the domain for x tilde, and which maps to which map delta maps from 0 to infinity and is strictly decreasing, continuous and bounded function. Okay. So, these are the three qualities: strictly decreasing, continuous and bounded, such that delta t tends to 0 as t tends to infinity. No periodicity of the dynamics is assumed here. Okay, so, this is the basic definition. Now, consider the proposition you can look into the book Hassan Khalil, double S or single S is there, I do not remember, but this is Hassan Khalil by on non-linear systems. Non-linear systems. Okay. In this book you will find this definition. Moreover, this proposition which I am stating here, this is also given in Khalil. So, these are the basic things required to prove the system stability. So, proof is given there. You may not be aware of all these things. It is quite possible that you have not gone through the Lyapunov stability analysis for the nonlinear system. You might have done it for the linear system, but still as an effort I am putting it here, so that this topic gets completed, and I will put this proof as the supplementary material. So, consider the system where f is a mapping from 0 to infinity. This is about t, and then the domain D for x tilde, the epsilon 0, this is less than 1, okay, and it maps into R n. So, the function f, it maps from, these are for the 3 items which is appearing here, 3 variables. This is basically a vector x tilde, but t is a scalar, epsilon is also a scalar. So, the corresponding 3 domains are here. So, from there it is a map to R n. So, n dimensional space, okay, n dimensional real space. So, f is continuous and bounded up to the second order with respect to x tilde and epsilon. So, what we will do, we will change it to this one. If we are taking this f to be to have continuous bounded partial derivatives up to second order with respect to x and a tilde. So, your domain must not be closed. If it is a closed domain, so that means if I have a point here, so I cannot have neighborhood of this on this side. Here the neighborhood is there in this domain, but this side we cannot have neighborhood. But if the domain is open, which is always shown like this, so you can take any point as close as to the boundary, but there will be always a neighborhood of that. So, this is important in this respect. So, the epsilon lies in this range, and therefore, your system will be then differentiable with respect to, or the will have partial derivative with respect to x tilde and the epsilon. So, both this and this we make it open. And the proper way of defining this is that the systems the domain should be open, but in the case of the t, it so happens that you start your t equal to 0. So, always there is a starting time. So, you will have the left hand side as the closed one. So, thereafter in the time, at any instant of time, you are looking into the differentiability of the system. So, therefore, I initially inserted this large bracket here. So, otherwise if you look from this point of view, so both of them should be the open set, and it is called the open connected set. So, those definition you should not go into, just look into this part, and then because some of the things may be beyond your reach right now. Suppose that f t x tilde 0 has an average function f average x tilde on 0 to infinity and on d. because this is for t and this is for x tilde, and the Jacobian so H is being defined like this, has the 0 average with respect to Jacobian of this has 0 average with respect to the same convergence as function same convergence function as f. So, the solution will obviously contain this t. So, therefore, t is appearing and this is for the averaged one. So, once you average it, so this t will get eliminated and it will appear in this format. So, if at the origin this value is 0 for all t epsilon element of 0 to infinity, times 0 to epsilon to epsilon 0. And the origin x tilde equal to 0 of the average system So, if the of the average system this origin is exponentially stable, then exists a positive constant epsilon star such that for all epsilon lying between 0 and epsilon star, the origin of the system epsilon will be exponentially stable. Okay, so, if your average system, what is telling that this theorem, that if your average system is this one is exponentially stable, then your actual system, this is a this is a non-autonomous system. So, the but casted in this special format, a standard format, then this will be also exponentially stable, means its origin will be exponentially stable. So, that implies if this is the origin and say this is the phase space x 1 x 2. So, in the neighborhood of this, the system will decay exponentially to the origin, this is what it implies. Okay, but in the neighborhood it does not talk about the it is a global globally exponentially stable. So, these are the issues which we deal in the nonlinear system controls. Okay, so, there is no time to discuss the details of all these issues. Okay, so, even if you are not aware of the nonlinear control system or its how to do the Lyapunov stability analysis, but if you take it for granted that this is the theorem and it goes like this, okay, then you will be able to understand some of the things which I am going to upload you, okay, upload on the internet. So, here we have, once we have got this, that this is once we average the system. So, this is at least locally exponentially stable, and then the theorem I will be providing you, that says that the system will be globally stable. Now, already we have proved that the system is on an average, it is controllable irrespective of whatever be the angular velocity of the satellite, arbitrary high, it can be anything less than infinity. So, theoretically it remains controllable, okay. And therefore, on an average the system will also be can be stabilized. So, this using this theorem, okay. So, this is locally exponentially stable and also the system will be globally stable, which will follow in the proof that I will upload, okay. But not globally exponentially stable, okay. It is only globally stable. So, anywhere you take the system, so it will remain stable. Okay. So, another proposition is okay, the system dynamics we are describing in terms of I times omega tilde dot equal to s omega tilde, I omega tilde and so on, and the kinematics we have described as q tilde equal to r q tilde times omega r tilde. So, this your system is given, system dynamics of the magnetically actuated satellite. And the control law minus epsilon square k p times q r tilde plus epsilon times k b times omega tilde r, where t is greater than 0. Okay, so we were talking about the let me state again, we are talking about the open domain. So, this is your open domain. So, in the x also x varies from in the phase space, let us say this is the 2 dimensional phase space in x 1 and x 2. So, on the outer side this is, you can see that here already you have the 0, okay. And then the outer side on the boundary, if you go on this side. So, let me state like this, because this is an important point. I have a point here. So, I will have a neighborhood of this. This is never closed, like if I take some interval on the right hand side, let us say this goes as 9.99, 9.999, 9.9999, okay, and so on. So, this is never closed. On the right hand side, though the upper bound is there, the upper bound will be 10, okay, but that 10 is not part of the system, this domain. Okay. So, you will always have wherever you go. So, if you take 9999999 something like this. So, still on the right hand side you will find points, and also on the left hand side there are points. So, in the 2D similarly, wherever however close you go to this particular dotted line. So, you will find a neighborhood of this. On the left hand side there will be there, on this side and this side also. So, therefore, you can ensure that the system is differentiable towards near the boundary, okay. And therefore, this is kept open. This is the significance, otherwise your system will not be differentiable on the near the boundary. So, if we are given this system and the control law, this is the proportional differential control law. Only thing, this one, the extra term epsilon square and epsilon, they are appearing. Okay. So, using this law, you can recast this system in this format, x tilde equal to epsilon and then this can be averaged to get a form epsilon f average x tilde, and which can, to which the Lyapunov stability analysis can be applied. Okay, so, given this, where t is greater than 0, where so this you can remove, this is not part of the statement of the theorem. So, where q tilde r is the vector part of the quaternion, renders the origin So, this is basically your 0 0 0, the equilibrium condition of this origin. So, given renders the origin of the closed loop system described by x tilde dot equal to f x tilde and so here in this case you have averaged it out. So, everything is appearing in the form of u is a function of x, the state variables, and therefore, this is appearing in this format. Okay. So, this includes your dynamics and kinematics, and u tilde this equal to minus epsilon square k p times q bar tilde k b times omega tilde r. So, the closed loop system is described by this. U goes into the, you remember that we had the term gamma u. So, this gamma tilde u, you are replacing by this. Okay. So, then it becomes a closed loop system. So, that closed loop system is locally exponentially stable for t greater than t 0 . Moreover, all the trajectories of this system, okay, of this system converge to q bar 0. When the origin is achieved, when the body frame coincides with the orbital frame, means they become parallel, x 0, y 0 and z 0, and they are both at the same location. I am just showing it differently, and this is x b, y b and z b. It becomes like this. With the orbital frame, that is q tilde, this becomes equal to q bar 0 0 0 1. So, here q bar you can add 1 also. So, this is the scalar part of the quaternion. That means, this simply implies that q tilde r, this becomes 0 0 0. or equivalently q tilde r, this will be 0 0 0 transpose. So, this is the origin of the system. So, system will converge to this. Now, the problem is of reducing your actual system, which is governed by, which is written like this, to a format, say, which can be shown it like this, z tilde t epsilon. So, we have to reduce it here into this format, okay. And for that you need certain substitution. So, I am not going through all the things, just I will give you the initial part and then I will upload the material. So, a linear transformation is applied and we define m 1 tilde as q tilde, m 2 tilde is equal to omega tilde divided by epsilon, m 1 r tilde equal to q r tilde, this is the scalar part of the quaternion. So, these are some of the transformation relationship we have to use to reduce our system into the required format. That means, you are given I times omega tilde dot s omega tilde I omega tilde plus t gravity gradient plus gamma times u tilde, and this disturbance we can ignore here. Okay, that will facilitate simplicity of the derivation. So, now here what is required, say this is the omega tilde. So, omega tilde, if you write here, omega tilde is epsilon times m 2 tilde. Omega tilde dot, this will be epsilon times m 2 tilde dot. M 1 tilde, like the M 1 is q tilde. Okay. So, this implies M 1 dot will be q tilde dot, and which is nothing but r times q tilde times omega tilde r and r q tilde, and omega r is from this place, here in this place epsilon times m 2 r tilde. So, this gets reduced to epsilon times r q tilde times m 2 r tilde. So, this is your m 1 tilde dot. Okay. So, this way all the terms are to be worked out. Okay. And if you do that, so your this equation, this will get reduced into this format. You can try it yourself, this exercise, at least this is easy. Three m 0 square, instead of omega square, this becomes m 0 square. And plus your epsilon times gamma k p times r tilde minus k b times m 2 r tilde. So, this particular term earlier we have written as gamma times u. So, you have defined as epsilon square k p times q r tilde minus epsilon times k v times omega r tilde. Q r tilde from this place, this is this part, q r tilde equal to m 1 r tilde. So, this is m 1 r tilde minus epsilon k v times omega r tilde is written here. So, this is omega r tilde, this becomes epsilon times m 2 r tilde. So, this is epsilon times m 2 r tilde. Okay. So, this becomes minus epsilon square k p m 1 r tilde plus k v m 2 r tilde, and then you are multiplying it with gamma. So, this becomes minus epsilon square times gamma and k p m 1 r tilde plus k v times m 2 r tilde. Okay. Okay. And then your this particular part I times omega tilde, this can be written as I times epsilon times, here this is epsilon times m 2 tilde. Okay. So, this is epsilon times m 2 tilde. So, you can see that m 2 tilde dot. So, this becomes, and epsilon is taken outside. So, if we, this is on the left hand side, on the right hand side you have s omega tilde and all those terms. So, these terms need to be converted, okay. But here I am particularly taking this term. So, this term appears as minus, other terms I am not considering here for simplicity. That will follow up in your the uploaded material. M 2 r tilde. So, if you see here this epsilon it will cancel and you will get this as m 2 tilde dot, this equal to some other terms minus epsilon times gamma times k p m 1 r tilde plus k v m 2 r tilde. Now, go back and look here in this place, is it the same thing? Okay. So, minus sign only thing here I have kept it here inside. Okay. Here in this place I have brought it outside. So, it is the, so this equation. So, in this format what we see that if I take this I on the right hand side. So, you can see that this will be of the form m 2 tilde equal to, this will be a function of m 2 tilde and other variables which are involved. Okay. So, and epsilon is here outside. Okay. So, this becomes reduced to, this gets reduced to a form where the averaging can be applied, because here in this case this is a term which is less than 1, which is small, and therefore, the it makes it casts the system into a form where the dynamics is varying slowly as compared to the excitation. If we look into the body frame, however fast the, as you make the body rotate as fast as possible. So, the dynamics of the body it is a getting accelerated, it is a becoming very fast, say its angular velocity has become very high. So, does the excitation becomes high, because the your magnetic field is in the orbital frame and from there you are converting into the body frame. So, that also changes in that case. So, that components of the magnetic field in the body frame will also change. So, here the excitation becomes also very high. So, if you speed up the body, so the excitation will also speed up. Okay. So, this averaging will always be can be applied, and therefore, this has got reduced to a standard format, and thereafter it is just a matter of construction of a Lyapunov function. Okay. And if we do that, then the system stability proof can be proved, and so the Lyapunov theorem, Lyapunov function can be chosen like this. Okay, I am not going to derive this part, I am going to upload this material. This is E tilde B x, this is the first column of your attitude matrix, and E tilde B z, this is the third column of the attitude matrix. So, basically this term is appearing for the gravity gradient consideration. Okay. M 0, this part we have written. Forming Lyapunov function, this is the Lyapunov function, I have briefed you earlier about this. Lyapunov function is a function where V 0 equal to 0 and V x tilde this will be greater than 0. So, it is a positive definite function. Okay. However, if we and if V dot x, if this is less than 0, then we say that the system is asymptotically stable. If V dot x is less than equal to 0, so this is asymptotically stable. And this is stable in the sense of Lyapunov, in the sense of Lyapunov. So, I am not going into this theorem, I am presuming that you know all these things. Okay. But if we apply Lassalle's theorem, so in the Lassalle's theorem, this condition that V 0 equal to 0, this is relaxed. Okay. And moreover, V dot x less than equal to 0, this can also ensure that the system is asymptotically stable. You can look into Khalil for all these things. Okay, so, here in this case, for sufficiently large K p, V will be greater than 0. Okay. It can be ensured that V is positive definite. So, for sufficiently large K p, it can be ensured that V is positive definite. And so, we will follow rest of the things in the material to be uploaded. You can check that at the origin. So, at the origin M 2 r will be 0. So, this term will vanish. Okay. At the origin your body frame coincides with the orbital frame, and therefore, your attitude matrix A q will have, it will be just an identity matrix. Okay. So, your E B x first column of this becomes 1 0 0. So, this can be reduced to a format, and I is your inertia matrix. Okay. So, this also gets reduced to 0, you can verify. The same way this also gets reduced to 0, and at the origin, because your q 4 equal to 1, okay, and q r tilde this equal to 0 0 0, and this is nothing but q 4 equal to m 1 4 we have defined. Okay. So, therefore, this also becomes 0. So, that at the origin it is ensured that V 0 equal to 0, and rest everywhere this is one negative term, but it can be ensured that if you keep K p quite high. So, for irrespective of the state of the system, this V can be made positive definite, and for this the condition can be defined accordingly, which will follow up in the materials to be uploaded. So, this way we have discussed about the system stability, and it can be shown that V dot x this is less than 0, okay, less than equal to 0. So, using the Lascelles theorem, then it can be shown that such a it can be stated that such a system is globally asymptotically stable, because there it happens that for any state it can this is satisfied. Okay. Means anywhere you leave the system in the state space, it will converge to the origin. Okay. So, what we have discussed about the magnetic attitude control. So, basically we have not gone into the design of the coil or the magnetic torquer, because my objective is not to teach you the how to make the torquer and other things, but basics of the magnetic actuator, how does it work, how to apply it to the system, and how the control is done. So, this way it comes to an end, and using the magneto-coulombic system, which is the using the charge also, the system can be controlled. So, some minor changes in this is required, the equation remains same almost, and then the proof of the theorem remains same. Okay. And only thing in the dynamics part, in the torque part, the equation, the torque equation will differ, okay, that we need to derive. So, if I find time, so I will do that, otherwise we wind up here in this place today, and we will continue this. Then we are left with the aerodynamic torque and solar radiation torque. Okay. So, these are basically taken as disturbance to the system. Okay. And if you are looking for a particular control, that just using the aerodynamic torque you want to control. So, once your force is calculated, okay, so the torque can be calculated, and using that torque. So, you gravity gradient is present, suppose, because gravity gradient will always be present until unless you are in the satellite is in the geostationary orbit, the gravity gradient will be always present. We will continue in the next lecture. So, thank you very much for listening.